Now we have example 4 from lecture 1. In here we've given the production function and price function. They're listed right here. So this would be our production function, and this would be our price function. And we're going to answer the following questions. Calculate the marginal revenue when labor L is equal to 30. By definition, we know that marginal revenue is equal to the change in revenue with respect to the change in quantity. So when we talk about marginal revenue or marginal cost, it's always with respect to quantity, the DQ, by definition. So here we want this derivative of revenue with respect to quantity. Well, we don't have a revenue function, so we have to figure that out. So revenue is going to be the price per unit times the quantity sold, PQ, and we want this in terms of Q, not in terms of labor. So we have price, negative 0.1 Q plus 70, that was given to us right here, times quantity Q. I'm going to FOIL this out, so I'm going to multiply negative 0.1 Q times Q, giving me negative 0.1 Q squared, and 70 times Q gives me 70Q. So now I have a revenue function. Next step, I'm going to do the derivative of this with respect to Q. Unfortunately, my function is already with respect to Q. So I simply do the derivative of this function. For my first term here, I have negative 0.1. Then I do the derivative of Q squared. So I pull back the 2, and I have Q to the power of 2 minus 1 is 1, or I just leave that blank. And then for my second term here, I have the derivative of 70 as my coefficient. So it just goes along for the ride, times the derivative of Q. That's Q to the power of 1, so that simply becomes 1. Cleaning this up, I have negative 0.2 Q plus 70 as my derivative for the marginal revenue. So that's the derivative, but that's not what the question asked for. It asked for the marginal revenue when L is equal to 30. Now I have no L terms here. I have Q's, but I do know how to calculate Q if given L. So I'm going to take my function here, Q is equal to 200L minus L squared divided by 20, and substitute L is equal to 30 into that equation. So I have 200 times 30 minus 30 squared all over 20. And what I get when I do that is 255. And the reason I did this was so that I could have a Q value to insert into my marginal revenue function, the Q value for when L is equal to 30. So now marginal revenue when L is equal to 30, which means that Q is equal to 255, is going to be equal to negative 0.2, and I have a Q value of 255 plus 70. And this gives me 19. And that's my answer. Marginal revenue when L is equal to 30 is 19. Now onward to part B. Just going to erase some of these. Part B, calculate the rate of change in production with respect to labor when L is equal to 30. I'm first going to focus, I'm going to ignore the L is equal to 30 part and just try to look at what rate of change in production with respect to labor implies. So this is the definition of a derivative, a rate of change in one thing with respect to another. So rate of change of production, production is Q, with respect to labor. So change in production is represented by DQ, that marginal change, with respect to the change in labor. In other words, as labor goes up by 1, how much change in production do we expect? To do this derivative, I'm going to need a production function. and I want it in terms of labor in order to be able to do the derivative, or I'll have to do some other fancier stuff. That is given to me already right here, so I'm going to rewrite it down here. It's 200L minus L squared all over 20. Now, before I go about doing this derivative, I see that I have a fairly simple denominator. It's just one term. So I like to split it up. I like to split up my function so that I can get rid of that common denominator. So I'm going to write it as 200L divided by 20 minus L squared divided by 20, which is going to give me 10L minus 0.05 L squared. So that is the same production function, just written in a way that's going to be a little bit easier, at least for me, to do the derivatives of. Now what I'm looking for is my derivative dq by dl, and my function for q is already in terms of L. So I've got this laid out for me in a pretty ideal form. So I'm going to do the derivative of my first term here. 10 is the coefficient. It just goes on along for the ride. And then I do the derivative of L to the power of 1, which anything to the power of 1, the derivative is 1. And then I'm going to do my second term here. Negative 0.05 is my coefficient. It just goes along for the ride. And then I do the derivative of L squared, which is 2L. Cleaning this up, I get 10 minus 0.1L. And that's my derivative dq by dl. Now, I want a little more than that. It's asking for me to solve for when L is equal to 30. So now looking at this, that means when L is equal to 30, I need to substitute that into this expression. So dq by dl when L is equal to 30, which, by the way, is the same thing as when Q is equal to 255. I learned that in part A, though it's not necessary here, is going to be equal to 10 minus 0.1 times my L value of 30. This gives me 10 minus 3, or 7. So I have 7 as my derivative, dq by dl. Alternatively, we would say this as the rate of change in production for every unit increase in labor. And then there was a third part to this question. Just going to erase this up here, and that is to calculate the rate of change in revenue with respect to labor when L is equal to 30. So again, ignoring my L is equal to 30 for now, just trying to dissect the language. Rate of change in revenue with respect to labor. So we have rate of change in revenue, that marginal change in revenue, with respect to labor. So with respect to a change in labor, or for a 1 unit increase in labor, what the expected or approximate change in revenue would be. So now, to do this, it's going to be a little bit trickier because the revenue function I developed earlier. So I came up with a revenue function earlier, and it was negative 0.1 q squared plus 70q. Let me rewrite this over here. Negative 0.1 q squared plus 70q. Now I want the derivative with respect to labor, but as you can see here, my function is with respect to q. So I cannot directly, at least, do the derivative. There are two approaches I could take. The first approach is I could take this revenue function, r is equal to negative 0.1 q squared plus 70q, and wherever I see these q values, I can sub in q is equal to 200L minus L squared divided by 20. As a reference, that's the information we were given to begin with right here. So I can substitute that into this expression. I would get revenue is equal to negative 0.1 times 200L minus L squared over 20 all squared plus 70 times 200 L minus L squared all over 20. And then from here, I could figure out what that derivative dr by dl is. And that's a little bit of a nasty derivative. So I'm not sure I want to do this. Ugh. If I have to, I could. But if I don't have to, if there's an easier way, why wouldn't I take it? So let's think about what the other approach. I said there's two approaches. Maybe the other approach is more enticing. And that is leveraging info on other changes. As again, a reminder, dr by dl is what we're going for. And what this implies is, what change do we expect, or approximate change, I should say, in revenue is expected with a 1 unit increase in labor, L. That's our R. That is really what it's asking. What we determined in part A was that the marginal revenue, which by definition is dr by dq, and we determined that value to be 19. So what this tells us is that as Q increases by 1 unit, we expect that R will increase by approximately 19 units. That's what that means by definition. And in part B, we learnt that dq by dl was equal to 7. And what that means is that when L increases by 1 unit, we expect approximate change in Q of 7 units. So let's try to connect this information into what we're trying to get over here for dr by dl. dr by dl, let's see how that relates. So what this is saying is that L is going to increase by 1 unit. We're trying to approximate the change in revenue. But what we do know is that if L increases by 1 unit, we expect Q to go up by 7 units. So that's from here. And from here, we know that if Q goes up by 1 unit, we expect revenue to go up by 19 units. So if Q is going up by 7 units with a 1 unit increase in L, this implies 1 unit increase in L, how much will revenue increase by? Well, we can multiply that 19 times 7. If it goes up by 19 for 1 unit increase, L goes up by 1 unit, Q goes up by 7, R goes up by 19 times 7. So we can calculate dr by dl is going to be equal to, and please note that all of this was for when L is equal to 30. When L is equal to 30. When L is equal to 30. And we're trying to figure this out for when L is equal to 30. So dr by dl is going to be equal to 19. That is our dr by dq times 7, which is our dq by dl. And that will give us 133. So that is going to be our dr by dl. This is when L is equal to 30. But we can extend this principle. This is the essence of the chain rule. This is the essence of the chain rule, that we're looking at how the change in one unit, in this case Q with respect to L, but we're really interested in how revenue changes with respect to L. But if we know how revenue changes with respect to Q, and we know how Q changes with respect to L, well, then we can figure it all out. This is dr by dq times dq by dl. And you can see that there's kind of like this pseudo cancellation that kind of happens there, leaving us with r over l. And that is the essence of a chain rule. So that if you can figure out how these relative changes occur and they're linked, you can get different types, you can approximate different types of changes. So in the end, we could even write this as an expression. dr by dl would be our dir by diq, which was given to us, over here, negative 0.2q plus 70, times dq by dl, which we had over here, 10 minus 0.1 L. And I know this is in two variables, so we can know that Q is equal to 200 L minus L squared over 20, but we can solve for this for any level of labor. We can solve for the change in revenue with respect to labor. Now, that's a pretty complicated concept, but it is also a very important concept. It gets used quite a bit in the world. If you ever enter the world of trying to do anything in coding, it's going to be there a lot, but it's also going to be there in economics. So this is a pretty important concept of how the chain rule applies. That if we know the value of dr by dq and the value of dq by dl at the same level of labor, so this was dr by dq was determined at the same level of labor, then we can go directly to dr by dl. So this is an important enough concept that I also want to show it graphically in case that resonates even better. So the first image I have here is for production versus labor. So that's our Q value we see on the vertical axis and our labor value on the horizontal axis. And here we are at labor is equal to 30. And when we're looking at a derivative, it's saying, what is that tangential line right here? So it's doing an approximation of that change for a 1 unit, let's say that's about here, change in labor. So we can see that it's increasing, and that derivative we should thin out my pen here, dq by dl, this was saying, we determined that this was 7 in part B, saying that as labor goes up by 1, we expect Q to increase by 7. And when I calculated this, because I drew out the function using our production function, Q is equal to 100 L squared minus L squared all over 20. This value right here was 255, and it goes up to 261 after 1 unit increase in labor, 261.95 for when labor is equal to 31. And when labor is 30, it's equal to 255. So you can see that it actually has a change of a real change of 6.95. And what our derivative does, it gives us an approximate change, saying it's that change for 1 unit of labor, that change in quantity is going to be approximately 7. So you can see that it's pretty close to what the true change in quantity was. So essentially we expect quantity to go up by 7 units as labor goes up by 1 unit. And that's the beginning of our estimation process. Now the next thing, the next graph I have here is revenue versus production. So now revenue, that's what we're really focused on, versus production. So when we start, we have a Q value of 255 when L is equal to 30. L is equal to 30, therefore Q is equal to 255. So that is somewhere right around here approximately. And what this is saying, we got the derivative dr by dq was equal to 19 when q is equal to 255. So that's saying when we look at the change here, for a 1 unit increase in quantity, which is going to be really itty-bitty here. So it's so itty-bitty, in fact, that I can't even draw it. But at this place right here, if I were to zoom into it, what it's saying is that for a 1 unit change in quantity is equal to 1, we would expect a change in revenue of 19. But you can see from this scale, where this is 50 units wide, it's really hard to show what just 1 unit change will be. But we can expand on that, because what we said earlier is that if labor is changing by 1 unit, our Q is changing by 7 units. So let's look at what this is times 7 units. If the change in Q becomes 7, we just multiply that ratio by 7, and we get 133. And so what we're saying is that when it goes from 255 to 255 plus 7, so 255, our revenue, when Q is equal to 255, our revenue is $11,347.50. I previously calculated this. And when Q goes up by 7 units, so 7 units, that brings us to 262. Q goes up by 7 units, we would expect an increase in revenue of 133. So we're going to add that on to 11,347.5, giving us a revenue of $111,480.50. Now, let's compare what really happens, and that is when labor increases from 30 to 31, revenue increases from $11,347.50 to $11,474.72. That's what actually happened, as opposed to the 133 approximate change. And that change is $127.22. So you can see that it's not an exact value, but it gets us really close to what that value is. And the larger the change, so we had a change in Q of 7, that larger that change, the less exact our change will be in revenue, our estimate of that change, but it's still very much close to what we expected. So that's a very good estimate.